Welcome to Tomorrow Unveiled. Have you ever considered how the future might be powered not just by clean energy, but by sources that are also incredibly powerful, reliable, and, well, remarkably compact? This past week delivered some truly groundbreaking news that suggests a fundamental redefinition of our global energy landscape.
It really does. It feels like a profound shift is underway. The conventional thinking around clean energy, it's evolving fast, driven by new demands, urgent demands, and a policy environment that's changing significantly.
And that's exactly what we're diving into today on Tomorrow Unveiled. Our mission is to unpack these latest energy developments, focusing really intently on this accelerating trend toward high-density power. We'll explore why technologies like advanced nuclear and, yes, fusion are now making such massive strides and what this actually means for our energy future. And we're drawing all this from the comprehensive research compiled by our dedicated research team.
That's right. And the core insight from that research is, I think, pretty clear. We're moving beyond just low-carbon energy. There's this urgent, almost desperate demand emerging for power sources that are firm, consistently reliable, and physically compact. This is the very essence of our theme today. Green code, hot core.
Green code, hot core. I like
Yeah.
that. It perfectly captures this pivot.
Yeah.
So what's genuinely driving this powerful push towards these high-density solutions right now?
Well, two major forces are really pushing this. First, we're seeing just an exponential surge in electricity demand, especially from the insatiable appetite of artificial intelligence and the colossal data centers needed to house it. And second, there's a new, much more pragmatic policy environment taking shape globally, one that prioritizes immediate grid stability, energy security, and, frankly, industrial competitiveness.
Right. And what our team uncovered, which I found fascinating, is how interconnected this all is. This week's events, they aren't isolated incidents, are they?
Not at all.
They're all part of a clear converging trend towards these high-density solutions. It's almost like the future is, I don't know, literally consolidating its power sources.
Precisely. Speaking of the future, let's jump into some of the most exciting breakthroughs from this past week, starting with nuclear fusion. I mean, for decades, fusion was the punchline, right? Always 30 years away.
Yeah, always just over the horizon.
This week, it felt a whole lot closer.
It really did feel like fusion jumped from the lab bench straight to the investors' boardroom this week. The biggest news has to be the Google Commonwealth Fusion Systems Power Purchase Agreement, the PPA. Google committing to buy 200 megawatts from CFS's first planned commercial plant, targeting the early 2030s? Is this just symbolic, or does it genuinely move the needle?
Oh, it's a game changer. I really think so. Because we're moving from scientists pushing a technology forward, the old technology push, to major industries pulling it into commercial reality. This is the first direct corporate PPA in fusion history. It signals this pivotal shift to a market pull model where explicit demand from someone like Google is actively pulling the technology towards commercialization. It's huge.
And it's not just commercial deals either. The research we've gathered points out that CFS has actually joined ITER, the International Thermonuclear Experimental Reactor, their tokamak physics activity. That suggests a new era of public-private collaboration, doesn't it? Which I think has to be a significant accelerator for development.
Absolutely. Collaboration speeds things up. But it raises the question, what about the underlying fundamental research? Is that keeping pace? And this week brought more good news there, too. We saw record-breaking plasma containment times, both at Germany's Wendelstein 7X accelerator and the UK's JET tokamak. These weren't just incremental improvements. They were breakthroughs in holding that superheated plasma stable for longer than ever before. That's a fundamental challenge for fusion.
Holding the fire, essentially.
Exactly. Plus, there's this new symmetry theory approach that sounds promising. It could significantly speed up reactor design, potentially simplifying the incredibly complex magnetic fields needed that could shave years off development.
Okay, so fusion is leaping forward, but advanced fission, particularly with small modular reactors, SMRs, they aren't just walking, they seem to be absolutely running. What's powering their rapid rise in capital and contracts?
Well, the AI nuclear nexus is becoming incredibly clear. Look at TerraPower, Bill Gates' advanced nuclear company. They just secured a, $650 million funding round, and NVIDIA's venture capital arm was a notable investor. That's a powerful signal, isn't it? The tech sector sees SMRs as critical for AI's immense future power demands. TerraPower's Natrium reactor, for instance, is targeting 2030 operation out in Wyoming.
And just to put that in perspective, Microsoft also signed that huge 835 megawatt PPA. They're planning to revive 3 Mile Island Unit 1, of all places, specifically for its AI data centers by 2028. It's not just a vote of confidence. It feels like a statement that advanced nuclear is seen as essential for scaling AI.
Exactly. And beyond that specific AI link, there's just unprecedented global momentum for SMRs right now. The United Kingdom selected Rolls-Royce SMR as the preferred tech for its national program. They're targeting mid-2030s grid connection.
Okay.
Up in Canada, Ontario Power Generation is moving forward with SMRs at Darlington, and GE Vernova Hitachi is investing in a new engineering center there, too.
And in the U.S., no-scale power hit that crucial regulatory milestone. They got standard design approval from the NRC for their 77-megawatt design. That should significantly streamline future licensing, right?
It absolutely should. And we also saw GE Vernova, Hitachi, and Fortum sign an agreement to deploy BWRX 300 SMRs in Finland and Sweden. It's a truly global picture emerging.
It really is.
Yeah, and we even saw microreactor companies like Oklo and Nano Nuclear Energy making their U.S. stock market debuts. Investor interest is clearly growing right across the board for these advanced fission technologies.
That's a lot of incredible technological advancement packed into 1 week. But even the most reliable power needs a backup, especially for something as critical as, say, a data center. Which brings us to another high-density, essential storage.
Yes, and what's striking here is how specialized these solutions are becoming. Vertiv, for instance, introduced new high-density lithium-ion battery cabinets. These are specifically optimized for AI and high-performance computing data centers. They provide that critical, uninterruptible power supply, but in these really space-constrained environments you find in modern data centers.
And that's part of a broader trend, isn't it? Our research highlights increasing investment in AI-driven energy optimization, and obviously the ongoing advancement of battery chemistries, things like solid state and lithium sulfur, pushing for higher energy density.
Right. And on the grid scale, our team also noted that China just completed the world's largest vanadium flow battery system. So the push for density is happening at all scales.
Okay, so technology is moving fast.
Yeah.
But let's talk about the policy landscape, because that's where things get, well, really interesting, particularly in the U.S. There's this new legislation being called the One Big Beautiful Bill Act, or OBB Act.
Ah, yes, the OBBB. Signed July 4th, 2025.
This act seems to fundamentally reshape U.S. clean energy investment. It's being called a paradigm shift. What makes it so transformative?
It's really about its dramatically divergent timelines for different energy sources. The OBBB Act imposes a really accelerated phase-out of tax credits for wind and solar projects. They need to have started construction before July 5, 2026, or be in service by the end of 2027. That's soon.
Very soon. And in stark contrast.
In stark contrast, it provides a much more favorable and extended timeline for nuclear, geothermal, and clean hydrogen. Some provisions there extend credits as late as 2033.
That differential treatment, it's a very clear policy signal, isn't it? The government is picking directions here.
It absolutely is. And then you layer on the foreign entity of concern, or FEIOC rules. These are stringent. They deny tax credits to projects with significant ownership or material sourcing from countries like China, Russia, Iran, or North Korea.
Okay, and what's the real-world impact here? I mean, these rules apply broadly, but where do they bite hardest?
They pose a monumental challenge for solar and wind supply chains, just monumental. They are heavily reliant on Chinese components, as you know. Nuclear projects, while they are subject to FEIOC ownership restrictions, they're largely spared from the most stringent material sourcing rules. That gives them a distinct competitive and, frankly, logistical advantage right now under this act.
So what does this all mean for the market? The analysis our team put together suggests this act actively steers investment towards firm, dispatchable power. It prioritizes grid reliability and energy security over, perhaps, simple decarbonization metrics.
That's the read, yes. And the projections are pretty stark. Delays or outright cancellations for an estimated 28 gigawatts of planned wind and solar projects because of this act.
28 gigawatts. Just to put that in perspective for listeners, that's like taking the equivalent power for millions of homes offline, or rather, preventing it from coming online. That's a significant reorientation.
It is, and it contrasts sharply with what we saw from the UK this week, doesn't it?
Yeah, tell us about that.
Well, in the same week the U.S. went hard one way, the UK demonstrated more of a dual-track strategy. They're simultaneously supporting Rolls-Royce SMRs as a kind of national champion, but also launching a new strategy to, quote, kickstart an onshore wind revolution.
So they're hedging their bets, more or less.
Exactly. It's a very different approach from the U.S.'s more focused, some might say pointed, direction.
That's a lot of policy nuance to absorb. It really makes you think about how America builds its energy future from here. Okay, let's shift gears slightly and talk sustainability. When we say green code hot core, how green are these hot core technologies really? Let's start with fusion.
Right. Well, from a life cycle perspective, fusion reactors actually have a very low carbon footprint. It's comparable to maybe slightly higher than nuclear fission currently. A significant portion of those emissions are tied up in the initial construction, concrete, steel, complex components. So as the wider industrial economy decarbonizes, fusion's carbon footprint will naturally decrease further over time.
And the physical footprint is minimal, right? That's a key advantage. The research highlights that a fusion plant needs orders of magnitude less land than solar or wind. You gave the example. A 1,000-megawatt nuclear plant might sit on just 1.3 square miles, whereas a solar farm of the same capacity could need, what, up to 45 square miles?
Exactly. Huge difference. Plus, the primary fuel, deuterium, comes from seawater, which is obviously abundant. But what's truly remarkable, I think, is the waste profile. Fusion produces no long-lived, high-level radioactive waste, period. Its main byproduct is just inert helium gas.
Helium, like for balloons.
Pretty much, yeah.
Yeah.
The radioactive waste that is generated comes from the reactor's structural materials becoming activated by neutrons. But this is low to intermediate level waste, and it decays to safe levels in approximately 50 to 100 years.
50 to 100 years. That contrasts sharply with the hundreds of thousands of years we talk about for conventional fission waste, doesn't it?
Night and day difference. The main radiological challenge is managing tritium, which is radioactive hydrogen used in the fuel cycle, but it's contained in a closed loop within the plant. Robust containment is essential, of course, but it's a manageable engineering problem.
Okay, so fusion looks pretty good on the sustainability front, especially long-term waste. Now let's talk about the SMR dilemma. How do they stack up, particularly on safety and waste?
Well, a big plus for many SMR designs is enhanced passive safety. Unlike older designs that needed complex active pumps and cooling systems, many SMRs use natural forces, things like gravity, convection, natural circulation. This means if anything goes wrong, even a complete loss of power, the physics itself keeps the reactor safe and cool for extended periods, days, even weeks for some designs like the BWRX 300 without needing any human intervention or external power. That's a huge leap for safety and public acceptance.
That certainly sounds like a significant safety improvement. But I remember hearing there were some nuances with their waste profile. What's the debate there?
Yes, this is an important point our research team flagged. While SMRs produce the same types of waste as larger reactors used fuel, irradiated components, a notable 2022 Stanford-led study, suggested they might generate significantly more nuclear waste by volume per unit of energy produced.
More waste. How much more?
The study estimated anywhere from 2 to 30 times more by volume. It's due to their unique physics. Smaller cores tend to leak more neutrons, which can activate more surrounding materials and might lead to less efficient fuel burnup compared to large reactors.
Wow, 2 to 30 times more volume. That's a pretty significant difference, especially when we think about the challenges of long-term storage for nuclear waste.
It is, and it highlights that there are trade-offs.
And what about upstream impacts, like mining for fuel or the infrastructure needed?
Right, a large global fleet of SMRs, if that's where we head, will definitely require an expansion of uranium mining, which carries its own environmental risks, as you know. Furthermore, if SMRs end up being geographically dispersed, maybe closer to industrial sites or communities, our findings suggest they could potentially have a higher overall environmental impact than a single large centralized plant. That's mainly due to needing much more extensive transmission infrastructure to connect them all.
Okay, so it's a complex picture. If we connect this back to the bigger theme, the longevity of waste is a really key differentiator here, isn't it? Fusion waste decays in 5,100 years, relatively speaking. SMR, or large fission waste, that lasts for 10,000 to over 1,000,000 years.
That's the stark comparison. It's a critical long-term consideration in the sustainability debate.
Definitely something for policymakers and the public to weigh. Okay, let's briefly compare these high-density breakthroughs with the established low-density sources, solar and wind. It really feels like we're seeing truly diverging paths this week.
Absolutely diverging. Solar PV, for instance, continues its relentless march of, let's say, incremental efficiency gains. We saw announcements just this week like LONGi hitting a groundbreaking 33% conversion efficiency for a tandem cell in the lab,
Impressive number.
and AICO achieving 24.4% efficiency for a commercial module, which is also very good.
Those are impressive technological gains, no doubt.
Yeah.
But our research really emphasizes they have to be viewed through The sobering lens of that new U.S. policy environment, the OBB Act, the accelerated phase-out of tax credits and those stringent EOC rules, they create severe economic headwinds for solar,
Hmm.
right? It potentially diminishes the value of those efficiency gains if the project economics just don't pencil out anymore.
Precisely. The tech gets better, but the market gets tougher, at least in the US, under this new regime. And we see a similar story with wind power. The trend there continues towards scaling up larger turbines, repowering older sites. A good example mentioned in the research was the Mount Storm wind farm, increasing its capacity by 85% just by replacing 132 older turbines with 78 new, much more powerful units.
But again, that OBB Act, those compressed construction timelines pose a significant challenge for these big capital-intensive wind projects, don't they? They rely on stable, long-term planning horizons.
They do. It's a direct collision between the new policy reality and how these large infrastructure projects typically get financed and built.
So the underlying message here seems clear. High-density progress is characterized by these step-change innovations, high upfront capital, yes, but very low land use, and critically firm dispatchable power. And that's now explicitly favored by U.S. policy.
Right. And low density, conversely, is more iterative improvement, often lower capital per unit initially, but very high land use, intermittent power, and now, as we've discussed, significantly impacted, maybe even penalized, by current U.S. policy.
It's a clear strategic snapshot, isn't it? Diverging paths for energy investment, especially in the U.S.
Moving towards the outlook, then. The path to this high-density future, it involves navigating several hurdles, definitely. But the integration timelines, they're becoming clearer than ever before, I think.
So for SMRs, what are we looking at?
The first wave seems credibly on track for the late 2020s and early 2030s. We mentioned TerraPower targeting 2030 for Natrium, the UK's Rolls-Royce SMRs aiming for grid connection by the mid-2030s. This is moving from projection to actual project timelines very quickly.
It feels much more real now.
Yeah.
And fusion.
And Fusion Energy's timeline is, frankly, accelerating rapidly. CFS targeting the early 2030s for its first commercial ARC plant, now backed by that Google PPA. Expert commentary and, market analysis we've reviewed now widely suggests the first commercial fusion plants could actually begin operation sometime between 2030 and 2035.
That's incredible, considering the old 30 years away joke we just talked about. But what are the main hurdles still to overcome for these technologies to really scale?
Well, for fusion, the primary hurdles remain fundamentally technological and economic. It's about scaling up from these short-duration experiments lasting seconds or minutes to continuously operating cost-effective power plants running 2047. That requires solving some profound challenges in materials. Science finding materials that can withstand the intense conditions inside a reactor for years, plasma physics, and complex engineering. Things like mastering the closed-loop tritium fuel cycle efficiently and reducing the amount of power the plant itself consumes just to run.
Okay, big science and engineering challenges still for fusion and for SMRs. What's mainly standing in their way now?
For SMRs, the challenges are arguably less about fundamental science. The physics is pretty well understood, and more about economics, regulation, and importantly, social license. Key hurdles include navigating complex, sometimes lengthy licensing processes, especially for first-of-a-kind designs. Establishing robust supply chains, particularly for the specialized fuels some designs need, like high-assay low-enriched uranium or HALEU. And then there's managing public perception, gaining acceptance for new nuclear facilities, and critically, developing and citing permanent solutions for that long-lived nuclear waste we discussed earlier. That remains a major challenge.
We've covered so much today, from policy shifts to plasma physics, AI demand to waste management. If you had to pick one thing that truly stands out from this week, or maybe one challenge that still feels particularly daunting, what would it be?
Despite listing all those significant challenges, what's really striking from this past week is the unprecedented convergence of forces. It's creating this powerful momentum to actually solve those challenges. The market pull from the AI industry needing massive power, the major U.S. policy shift clearly favoring high-density energy, and these landmark commercial deals and technical breakthroughs we've seen, it's fundamentally improved the outlook for both advanced fission and fusion. It feels like a race now, a real race.
That convergence of forces, market pull, policy push, technological leaps. That really is the standout insight from this week's news, isn't it? The green code, hot core vision, it's no longer theoretical. It feels like an emerging market reality. And its development is clearly going to be a defining feature of the global energy landscape for the entire decade to come. Now, if you're finding this insightful, and we hope you are, please take just a moment to like this video, subscribe to Tomorrow Unveiled, and be sure to turn on notifications so you never miss an update on the future.
And if you happen to be listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It genuinely helps us reach new listeners and keep these conversations going.
Absolutely. And we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, please leave a comment and let us know what you think about this shift toward high-density energy. Is it the right path? What are your biggest questions?
And perhaps as a final thought to leave you with, consider how the accelerating energy demands of our technological future, driven by things like AI, aren't just shaping which energy sources we choose, but might be fundamentally redefining what clean energy truly means, pushing us towards solutions that are not just low carbon, but also densely packed with power and unwavering reliability. Something to think about.